Welcome back to The Explainer. Today, we are diving into something that is honestly one of the wildest challenges in tech right now, evaluating foundation models. You know how sometimes an AI just seems to get lazy out of nowhere or suddenly gets way smarter? Well, it all boils down to exactly how engineers are grading them behind the scenes. We're going to break this all down today using some incredible insights from Chapter 3 of Chip Huon's book, AI Engineering.
So how do you grade an AI? I mean, it sounds like a totally simple question, right? But seriously, think about it for a second. How on earth do you reliably grade something that generates completely open-ended answers? When an AI can whip up a poem, code an entire website, or summarize a massive 300-page book in literally seconds, well, we obviously can't just hand it a basic multiple-choice test anymore. The old ways of scoring, they're completely breaking down, and this whole new science of evaluation is stepping in to take its place.
Here is our agenda for today. 1. The AI evaluation crisis. 2. Measuring functional correctness. 3. Similarity and embeddings. 4. The AI judge. 5. Biases in AI judges. And finally, 6. Ranking and comparative evaluation. All right, let's jump in.
Section 1. The AI evaluation crisis. Before we can even look at the solutions, we really need to understand why grading these new models has turned into a full-blown crisis for engineers.
Okay, let's look at this absolutely brilliant analogy from Chip Huon's book. The basic idea here is that as AI gets smarter, evaluating it gets exponentially harder. Look, most of us can instantly spot if a first grader messed up their basic math homework. But what if you're asked to grade a PhD-level math thesis? Yeah, that is a whole different ballgame. When an AI summarizes a complex book, you can't just skim it to see if it kinda sounds right. You actually have to go read the book yourself, fact-check the claims, reason through it, and apply real domain expertise. The evaluation process has become unbelievably time-consuming. And this whole headache becomes super obvious when we look at how things used to be. In the old world of traditional machine learning, tasks were mostly closed-ended. An AI categorizing photos just had to say, okay, that's a cat or that's a dog. Boom, easy ground truth. But foundation models, they are living in an open-ended world. If you tell an AI to write a catchy marketing email, there are literally infinite correct responses. You simply cannot curate a master list of perfect answers to check it against. Plus, we mostly treat these models as black boxes right now, meaning we can really only judge them by watching what they spit out.
Section 2. Measuring functional correctness. So, how do engineers wrangle this open-ended chaos? They bring back the math. Exact, rigid measurements.
And that brings us to functional correctness. This is basically the ultimate no-nonsense metric. It asks one simple thing. Did the AI actually do the job you asked it to do? Let's say you tell an AI to write a Python script to find the greatest common denominator. You don't just read the code and go, wow, that looks really elegant. No way. You literally plug that code into a Python interpreter and run it. If you feed it the numbers 15 and 20 and it doesn't spit out exactly 5, the model failed. End of story. It's pure execution-based accuracy.
Now, long before AI was writing code for us, checking functional correctness was just standard practice on platforms like LeetCode. Today, it is an absolute cornerstone for AI evaluation. Engineers use benchmarks like OpenAI's HumanEval or Google's MBPP, which stands for Mostly Basic Python Problems, to test coding skills. There are others too, like Spider, BirdSQL, and WikiSQL, which specifically test if an AI can write flawless database queries directly from natural language prompts. It's a fantastic, super rigorous way to grade an AI, but as you can probably guess, it really only works for tasks where you can actually execute the output.
Section 3. Similarity and embeddings. Because what happens when it generates plain text? If we can't run a paragraph like a piece of code, how do we measure it exactly?
Well, if you happen to have human-generated reference data, like a perfect gold standard answer, you can actually measure how close the AI's generated response is to that ideal reference. Now, a pure exact match is strictly binary. It either matches word for word or it totally fails. But semantic similarity, that gives us a sliding scale, usually sitting somewhere between -1 and +1. It calculates how close the AI's response is to the reference answer in terms of its actual underlying meaning.
To pull off this semantic comparison, we have to turn text into numbers, specifically numerical representations called embeddings. Check out this diagram of the CLIP architecture here. It basically plots concepts in a massive mathematical space. So the mathematical embedding of an image of a guy fishing is plotted way closer to the text of fishing Ann than it is to the text fashion show. By calculating the physical distance between these numbers, which is called cosine similarity, engineers can mathematically prove just how closely an AI's open-ended answer nails the intended meaning.
Section 4. The AI Judge. Here's the catch, though. Gathering all that perfect reference data is wildly expensive and agonizingly slow. Which leads us to a massive shift in the industry, and honestly, the most fascinating part of Chapter 3.
Faced with the completely impossible task of having humans sit around grading millions of open-ended AI responses, developers basically threw their hands in the air and said, you know what, let's just have AI grade the AI. This LLM as a judge approach just exploded in popularity after GPT-3 came out, and it makes total sense why. It's blazingly fast, highly scalable, and ridiculously cheap compared to paying human graders. The absolute best part? It requires zero reference data to work in production. To give you an idea of how big this is, a 2023 report found that a staggering 58% of all evaluations on the LangChain platform were done exactly this way.
If you want to see how this actually works under the hood, take a look at this prompt template. An AI judge isn't just a raw model, it's a carefully crafted system made up of a model plus a highly specific prompt. You literally just hand the AI a set of instructions saying, hey, given this question and this answer, evaluate how good the answer is on a scale of 1 to 5. You can tell it to judge correctness, check for toxicity, or see if it's being repetitive. If you swap out the model or even just tweak a few words in that prompt, you get a completely different judge. It is incredibly versatile.
Section 5. Biases in AI judges. But you knew there was a but coming, right? Handing the grading keys over to subjective AI judges comes with some pretty serious risks.
Just like human judges, AI judges have some major blind spots. When you ask an AI to evaluate a bunch of different responses, it can actually be tricked by the formatting instead of the actual facts. Take position bias, for example. This is where the AI favors a response simply because of where it was placed in the list. Or recency bias. We humans do this all the time, right? We favor the thing we just saw last. Well, AI can analytically mirror those exact same psychological quirks right in its outputs.
But the most dangerous blind spot of all might be verbosity bias. This is wild. Research by Wu and Ajee back in 2023 uncovered a startling trend. Big models like GPT-4 and Claude 1 will frequently prefer a longer, wordier response, say around 100 words, even if it is packed with factual errors. They'll literally give that a higher score than a perfectly accurate, concise 50-word response. The AI judge just fundamentally equates length with quality. And that right there is exactly why engineering teams cannot rely purely on AI judges. They absolutely have to supplement them with human evaluation, and those exact methods like functional correctness we talked about earlier.
Section 6. Ranking and comparative evaluation. So, with all these different ways to score, engineers are ultimately just trying to answer one practical question. Out of all these different models, which one is actually the best fit for my application?
Chip Huyn lays out a really great way to think about how we rank these models. Basically, you've got two main choices. The first is point-wise evaluation. Think of this like a dance competition. You watch each dancer or evaluate each AI model totally on its own, you give it a score out of 10, and then you rank everyone at the end. The second method is comparative evaluation. Now, this is more like a head-to-head chess match. You pit two models directly against each other and simply ask, okay, which of these two responses is better? Lately, comparative evaluation is gaining massive traction. Why? Because it usually gives engineers a much clearer, stronger signal of preference than trying to assign some arbitrary number out of 10.
So, as we wrap up this explainer on evaluating foundation models, we're left looking at a landscape that is rapidly shifting under our feet. The old days of having a simple list of ground truth correct answers, those are totally gone. Today, we rely on functional correctness whenever we can execute the output, we use similarity math when we happen to have reference data, and increasingly, we lean on AI judges for literally everything else. But as we hand over the grading rubric to the machines themselves just to save time and money, I want to leave you with one final thought. If we rely on AI to judge AI, and these models just keep getting exponentially more complex, who is left to judge the judge? Thanks so much for joining me today, and keep exploring.